In today's video, we'll learn about angular speed and angular acceleration. When we measure angular speed and angular acceleration, we measure it in a unit called radians. And radians is a unit of angular measurement. So for an example, the displacement around a circle, also known as the circumference, has a value of 2 pi rad. Or we can say that 1 radian is equal to 1 revolution divided by 2 pi. And that the angle of a displacement can be found by taking the arc length divided by the radius, which must be measured in radians and is measured from the positive x-axis in a counterclockwise direction. So below we can see we can convert degrees to radians and radians to degrees by taking our degrees times pi divided by 180 degrees will allow us to convert our degrees into radians. And we can convert radians into degrees by taking radians times 180 degrees divided by pi will convert our radians into degrees. And to the right of our slide, we can see we have two examples where we're given a value in degrees and asked to convert it into radians. So we see we have 60 degrees, and by timesing it by pi over 180 degrees, we can convert it into radians and get a value of pi over 3. And then we can also convert radians to degrees. We're given a value of pi over 4 in radians and asked to convert it to degrees. So by timesing pi over 4 by 180 degrees over pi, we see that this will be equivalent to 45 degrees. Now that we understand the measurement of radians, we can define our angular displacement. An object's angular displacement is the difference in its final and initial angles. And the SI unit for our angular displacement is radian, or written as rad. And our change in our angular displacement is equal to our change in our arc length divided by our radius. We say an object has angular speed if the object is rotating, and its angular speed can be defined as the change in the angular displacement divided by our change in time. And the SI unit for angular speed is radians per second. And our instantaneous angular speed is defined as the change in our angular displacement divided by our change in time as it approaches 0. If our angular displacement is increasing, our angular speed will be positive. However, if our displacement is decreasing or rotating in a clockwise direction, our angular speed will be negative. If you look at our first example, we see that our communication satellites are put into an orbit whose radius is 4.23 times 10 to the 7th meter. The orbit is in the plane of the equator, and two adjacent satellites have an angular separation of 2 degrees. Find the arc length that separates the satellites. First, if we summarize the information we're given that the radius of the satellites from Earth is 4.23 times 10 to the 7th meter, and that our angular displacement is 2 degrees. And we're asked to solve for the arc length between the two satellites. We know that angular displacement is equal to arc length divided by radius. We can solve for our arc length by multiplying both sides by its radius to get the equation where our angular displacement times our radius will give us our arc length. First, we must convert our angular displacement into radians, since our angular displacement is given to us in degrees. So if we do so, we can convert 2 degrees into radians by timesing it by pi over 180 degrees. We see that our degrees will cancel, and 2 times pi over 180 degrees will give us a value of 0.035 radians. And now, since our angular displacement is in radians, we can plug into our equation where we see that our arc length is equal to 0.035 radians times our radius of 4.23 times 10 to the 7th meters, and that the value of our arc length, therefore, will be 1.48 times 10 to the 6 meters. In our second example, we have a gymnast on a high bar that swings through 2 revolutions in a clockwise direction in a time of 1.9 seconds. Find the average velocity of the gymnast. So we're trying to find the angular speed of the gymnast. We see that our angular displacement is 2 revolutions, and since it's in a clockwise direction, our displacement will be negative, and that our change in time is equal to 1.9 seconds. We can solve for angular speed since the change in the angular displacement divided by the change in time will give us our angular speed. And we know our angular displacement in time, we can solve for our angular speed. We first must convert our revolutions into radians. In order to do so, we have negative 2 revolutions. For 1 revolution is equivalent to 2 pi. So if we take negative 2 revolutions times 2 pi divided by 1 revolution, we see that our revolutions will cancel, and we'll get a value of negative 4 pi. So if we plug this into our equation for angular speed, we see that negative 4 pi for our angular displacement divided by 1.9 seconds will give us an angular speed that is equivalent to negative 6.61 radians per second. And we see that our angular speed is negative since gymnast is rotating in a clockwise direction. Finally, we see that changing angular speeds leads to an angular acceleration. And we can define angular acceleration by taking the change in our angular speed divided by our change in time, which is expressed in SI units of radians per second squared. And just like angular speed, our angular acceleration will be positive if the angular acceleration is in a counterclockwise direction, and will be negative if rotating in a clockwise direction. In our third example, it states, before a jet takes off, the fan blades of the engine are rotating with an angular velocity of negative 17.5 revolutions per second. As the plane takes off, the angular velocity of the blade reaches negative 330 radians per second in a time of 14 seconds. Find the angular acceleration, assuming it to be constant. So with the information we're provided, we see that our initial angular speed is negative 17.5 revolutions per second, and our final angular speed of the blades is 330 radians per second over a time period of 14 seconds. And we're asked to find the angular acceleration. So we see that angular acceleration is expressed as our change in our angular speed divided by our change in time. We're given our final and initial angular speeds, however they have 2 different units. So we're going to have to convert our initial angular speed, which is a negative 17.5 revolutions per second, into radians per second. So we know that 1 revolution is equal to 2 pi. If we multiply and divide this through, we see that the revolutions will cancel, which will give us a value of a negative 110 radians per second. Now that our initial angular speed is in radians per second, we can take the change in our angular speed, which is 330 radians per second, minus our 110 radians per second, divided by 14 seconds to get our angular acceleration. And when we solve for this equation, we see that our angular acceleration will be equivalent to negative 16 radians per second squared.